This is part 1 of videos for section 8.5, where we're going to be discussing partial fractions. Let's say we wanted to integrate a rational expression. You'll see that the majority of problems that we've looked at in chapter 8 have all been rational expressions or integrating rational expressions. And the reason is that they're hard, and there are lots of different strategies that you can use to combat that. So one of the things that we can do here is that we can factor that denominator. So we previously looked at a method where we would use completing the square, and that can be tricky, most definitely. So if your denominator is factorable, then partial fractions is probably the way to go. But the idea again is to factor the denominator, and this is our main goal when it comes to partial fractions. Our goal is using factors of the denominator we're going to rewrite the rational expression as a sum of a couple of different simple rational expressions. And then integrate each term in that sum one by one. So that is our overall goal in the process of partial fractions. So the idea here is to take something in this form, where we've got those factors in the denominator, and to rewrite it as some expression over x minus 2 plus some other expression over x plus 4. And the big job here is trying to figure out what do A and B need to be so that mathematically we have a justified reason that says that summing these two is equivalent to this original expression. And so it kind of goes back to getting a common denominator, right? So if we were to add these two fractions together, getting a common denominator would require us to multiply the numerator of this fraction by x plus 4 and the numerator of this fraction by x minus 2, and together those two numerators should add up to equal 3x. So that's the kind of thing that we're going to be doing here, where we're going to be solving for appropriate constants of a and b, so that when we do use that process of getting a common denominator, that it does in fact result in our original fraction. So I can run through that process really quickly, and then I will outline it for you step by step. But again, if I were getting a common denominator, I would have to take the numerator of the first fraction and multiply it by the denominator of the second, and then the numerator of the second multiplied by the denominator of the first, and then I could put it all over the product of those two denominators. Well, in this case, again, we want to just focus on the numerators, because we already know what the denominator is. It's the a and b that we're curious in terms of what each of those expressions should be. So I'm going to focus only on the numerator, and I'm going to write out this equation that says that 3x has to equal a times x plus 4 plus b times x minus 2. I'm going to go ahead and distribute both expressions. And it does get a little confusing in terms of what gets written first, the letter a or the variable x, etc. as you go through, and it really doesn't matter. But the idea here is that even though this is 3x, it's really 3x plus some constant 0. And so if I look at my x terms, I have two of them. I have ax plus bx. And then if I look at my constant terms, I have two of them as well. 4a minus 2b. So the idea here is that I'm going to be writing two equations, one for my linear term and one for my constant term. My linear term says that 3x should equal ax plus bx, and then 0 should equal 4a minus 2b. Well, if I factor the x out in this first expression, I can actually cancel it from both sides of the equation, divide it by both sides. So that I now know that 3 has to represent the sum of a and b together. And then I have another equation that says that 4a minus 2b must equal 0. So what we're actually going to be using is a lot of algebra here in terms of solving systems of equations to figure out the separation of a and b. So my system of equations, if I just rewrite them in a more friendly way, I'd have a plus b equals 3 and 4a minus 2b equals 0. There are lots of different ways to solve a system of equations. There's the substitution method, there's the elimination method, you can even use matrices. I'm going to use elimination here. I want these two to add up to be 0. So I'm going to multiply my entire first equation by 2, giving me 2a plus 2b equals 6. And then I'm going to add those two equations together. So that gives me 6a. This variable was eliminated, which is what we want, equals 6. And therefore, I know a has to equal 1. We can use this equation right here to figure out b, where it looks like b has to equal 2. So I now know what each of these partial fraction values should be in order to have an appropriate decomposition that does in fact represent this original fraction. So let me write that out. Okay, so the partial fraction decomposition for the example that we were just working on will be that a equals 1, so that's 1 over x minus 2, plus 2 over x plus 4, since we found out that b was equal to 2. And what we're claiming is that that is equivalent to 3x over x minus 2 times x plus 4. Now we won't do this every time, but just once. Let's just do a check to make sure that this is correct and mathematically it's sensible. So let's find a common denominator here. Again, I'm going to take the first numerator and I'm going to multiply it by x plus 4, and my second numerator and multiply it by x minus 2, and put it all over the product of those denominators. Simplifying and distributing, x plus 4 plus 2x minus 4 becomes my numerator. And you can see that I'll have some like terms that I can combine, and then my constants are going to cancel out. So it does work. Alright, and it should work every time unless you make some sort of arithmetic or algebraic error. But this process of decomposing the fractions in order to create some partial fractions is just the reverse process of getting a common denominator. So it does in fact represent the exact same expression as what you had to start off with. Let's take a look at the actual integration piece of this. So the idea was that this is too hard to integrate as one term, but we can write it as the sum of two terms. And with integration, if you have two things that are both being integrated and they're added together, you can separate it into two separate integrations, integrate them individually, and then add your answers. So if I integrate this first piece, it's going to be the natural log of absolute value of x minus 2. You might do a u substitution here, where you're letting u equal x minus 2, and then du equals 1 dx, so that you're really integrating 1 over u du, and then u is actually negative, 1 over u is the same thing as u to the negative 1, whose antiderivative is the natural log. So it's up to you whether you feel like you need to write out this piece. But we're going to do so many of these that I think you're just going to start to automatically see that this is going to be the natural log. Over here, this is the same thing, except that we can pull out that constant of 2 if we want. So it's going to be 2 times the natural log of the absolute value of x plus 4. And of course, it's an indefinite integral, so that gives me plus c. I can use log properties to combine the two terms of my answer. Log property says that if I'm taking the log of two terms and adding them, I can combine it into a single log term by taking the product of those two arguments. Also, constant multiples out front equate to powers of the argument. So altogether, within my absolute value, I have the natural log of x minus 2 times x plus 4 squared plus c. So that's the overall process of partial fraction decomposition. In my next video, what I'll do is I'll summarize the steps in more of a procedural step 1, step 2 situation. So you can watch that next video, or you can perhaps skip to video number 3 for this section and try another example.